Understanding the sounds of space requires us to first understand what sound actually is and what it isn't. On Earth, sound travels as mechanical waves through air, water, or solid materials. When you speak, your vocal cords create pressure variations that ripple through air molecules, eventually reaching someone's ear. But in the vacuum of space, there are no air molecules to carry these mechanical vibrations. The answer lies in recognizing that the cosmos is filled with other types of waves, radio waves, plasma waves, X-ray emissions, and gravitational waves. While these aren't sound waves in the traditional sense, they carry information about cosmic phenomena in patterns of energy and frequency. This is where data sonification becomes our cosmic translator. Scientists take these non-audible waves and convert their frequencies, amplitudes, and patterns into the audio range humans can perceive. It's not unlike how a radio converts electromagnetic waves into music, we're simply tuning into different cosmic frequencies. But sonification is far more than a novelty. Just as data visualization allows researchers to spot patterns in complex datasets by seeing them as graphs or images, sonification allows scientists to detect patterns, trends, and anomalies by hearing them. The human auditory system is exceptionally good at detecting subtle changes in pitch, rhythm, and timbre, skills that can reveal cosmic secrets hidden in raw numerical data. Each sound we'll encounter today represents a different type of wave, a different cosmic phenomenon, and a different chapter in our understanding of the universe's violent, beautiful symphony. Saturn's rings have captivated humanity since Galileo first glimpsed them through his primitive telescope in 1610. But it wasn't until the late 20th century that we could truly explore them up close, and discover they had a voice. The rings themselves are composed of countless particles ranging from dust grains the size of viruses to house-sized boulders of ice and rock. Most of these particles carry an electrical charge, ionized by the relentless bombardment of solar radiation and cosmic rays. Saturn is surrounded by a magnetosphere, an invisible magnetic bubble, that shields the planet from the solar wind. This magnetosphere is filled with charged particles, electrons and ions, that aren't fixed in place. They flow, drift, and interact in complex plasma dynamics. When the charged particles in Saturn's rings encounter this magnetospheric plasma, they experience the Lorentz force, an electromagnetic force that causes charged particles to spiral around magnetic field lines. This spiraling motion creates oscillations in the plasma itself, generating what scientists call plasma waves. These waves ripple through the magnetosphere like invisible tsunamis, carrying information about the ring composition, particle interactions, and electromagnetic environment. In 1997, NASA launched the Cassini spacecraft on a 7-year journey to Saturn. The probe carried a sophisticated instrument called the Radio and Plasma Wave Science (RPWS) detector, designed specifically to capture these plasma oscillations. The RPWS instrument was extraordinarily sensitive. It could detect lightning strikes in Saturn's atmosphere from thousands of kilometers away. It could register the faint electromagnetic whispers of Saturn's auroras. And as Cassini made its daring passes through the ring system during its grand finale in 2017, it recorded something unprecedented. Saturn's thinnest rings, the D and E rings, contain dust particles just 200 nanometers in diameter, roughly the size of a virus. When these microscopic grains collided with the RPWS detector at orbital velocities, they vaporized on impact, creating tiny puffs of plasma. The instrument captured these micro-collisions as electromagnetic bursts. The resulting audio, when played back, is haunting. It sounds like radio static mixed with ghostly whistles and eerie, descending tones, as if the rings themselves were whispering secrets across the void. This was one of Cassini's final gifts before the spacecraft plunged into Saturn's atmosphere on September 15, 2017, ending its 20-year mission. What the sound reveals: the plasma waves tell us about the density and composition of ring particles, their electrical properties, and how Saturn's magnetosphere interacts with its iconic rings. Each whistle and chirp is a data point about one of the solar system's most complex and beautiful structures. Our second stop takes us far from Saturn's elegant rings to something altogether stranger, Comet 67P/Churyumov-Gerasimenko, a rubber duck-shaped chunk of ice and rock tumbling through the darkness between Mars and Jupiter. In 2014, the European Space Agency's Rosetta spacecraft achieved what had never been done before. It rendezvoused with a comet and deployed a lander, Philae, onto its surface. But even before Philae's historic touchdown, Rosetta made an unexpected discovery. The comet was singing. Rosetta's magnetometer, MAG, and Plasma Consortium, RPC, instruments detected oscillations in the magnetic field surrounding 67P. These weren't the smooth, predictable waves scientists expected. Instead, they heard something rhythmic, pulsing, almost organic. The mechanism: as the comet travels through space, solar radiation vaporizes ice from its surface, creating a thin atmosphere called a coma. This outgassing releases water vapor, carbon dioxide, and other molecules that quickly ionize in sunlight, forming a cloud of charged particles around the nucleus. These charged particles interact with the comet's weak magnetic field and the solar wind, a stream of charged particles flowing from the sun. The interaction creates oscillations in the local magnetic field at frequencies between 40 and 50 MHz, far below human hearing. When Rosetta's team transposed these oscillations up by a factor of about 10,000, they heard something unsettling: a deep, rhythmic clicking and humming that fans of science fiction compared to the creature from Stranger Things, the Demogorgon. Why 67P's song was different: Rosetta had visited other comets before, but none produced this distinct sound pattern. Scientists believe 67P's unusual rotating double-lobed shape and its specific outgassing patterns create unique plasma dynamics. The rhythmic nature suggests a quasi-periodic process, perhaps related to the comet's rotation or localized jets of gas erupting from its surface. The sound is a sonic fingerprint, revealing information about the comet's composition, its rate of outgassing, and how comets interact with the solar wind. It's also a reminder that even small, cold objects in space can generate complex electromagnetic phenomena. The recording: when you listen to 67P's song, it sounds like something alive, a creature growling in the depths of space, breathing and pulsing with an alien rhythm. It's beautiful and deeply unsettling in equal measure. Now we leave the solar system behind and journey 250 million light-years from Earth to the Perseus galaxy cluster, home to one of the universe's most massive objects, a supermassive black hole containing 17 billion solar masses. This isn't just any black hole, it's one of the most powerful engines in the known universe, capable of shaping the evolution of an entire galaxy cluster. The Perseus black hole sits at the heart of the galaxy NGC 1275, surrounded by an immense cloud of superheated gas called the intracluster medium, ICM. This gas glows with X-ray radiation, heated to tens of millions of degrees by gravitational compression and the black hole's activity. But something unusual was happening in Perseus. NASA's Chandra X-ray Observatory, one of the most powerful space telescopes ever built, detected ripples in the ICM, vast concentric rings of slightly denser and less dense gas spreading outward from the central black hole like ripples on a cosmic pond. These ripples weren't random. They were pressure waves, essentially sound waves, traveling through the hot gas. How could scientists hear a black hole? Black holes don't emit sound directly, but their immense gravitational influence and the jets of matter they eject can create pressure waves in surrounding gas. In Perseus, The black hole periodically releases bursts of energy that compress and heat the ICM, generating waves that propagate outward at nearly 1,000 kilometers per second. Chandra's instruments measured the spacing between these ripples and calculated their frequency. The black hole was producing a wave with a period of approximately 10 million years. When converted to a musical note, this corresponds to a B-flat, but one that is 57 octaves below middle C, the lowest note ever detected in the universe. To make it audible, scientists had to transpose it upward by those 57 octaves, compressing millions of years of oscillation into seconds. The discovery of this B-flat was more than just a cosmic curiosity, it was a breakthrough that revealed one of the universe's most important regulatory mechanisms. To understand the significance, you need to understand the problem astronomers had been struggling with, the cooling flow problem. Galaxy clusters like Perseus contain vast amounts of hot gas, trillions of solar masses of material sitting in the space between galaxies. According to physics, this gas should cool down over time, losing energy through X-ray radiation. As it cools, it should condense and form new stars at a prodigious rate. But observations showed this wasn't happening. The gas remained hot, and star formation in these clusters was far lower than predicted. The answer was sound. The pressure waves generated by the central black hole carry enormous amounts of energy, enough to counteract the cooling. As the waves travel through the ICM, they heat the gas through a process similar to how sound waves can heat air, though on an incomprehensibly larger scale. The Chandra observations revealed that the black hole's song is a thermostat for the entire galaxy cluster, maintaining the temperature of the intracluster medium, and regulating star formation across billions of light years. The sound itself, when you listen to the transposed recording, it's a deep, guttural, almost tormented drone, a sustained note that rises and falls with unsettling harmonics. It sounds less like music and more like the groaning of spacetime itself under the weight of 17 billion suns compressed into a singularity. It's the sound of cosmic regulation, of a black hole conducting a symphony of galaxy evolution across hundreds of millions of years. The Perseus black hole's B-flat note represents a fundamental principle of modern astrophysics. Supermassive black holes are not just destructive monsters, they're architects of cosmic structure. Without the energy injected by black holes through jets and pressure waves, the intracluster medium would cool, collapse, and form stars too quickly. Galaxies would burn through their fuel in a relative blink of cosmic time, and the universe would look dramatically different. This process, called AGN feedback, active galactic nucleus feedback, is now understood to be one of the key mechanisms controlling galaxy evolution. The sound waves are the delivery system for this energy. Other galaxy clusters have since been found to have similar acoustic phenomena, each with their own frequency and character, suggesting this is a universal mechanism. The universe is literally humming with the regulatory influence of supermassive black holes. But these are still just pressure waves in gas, variations in density detected as X-ray emissions. Our final stop will take us to something far more fundamental, the warping of spacetime itself. In 1915, Albert Einstein published his theory of general relativity, revolutionizing our understanding of gravity. In Einstein's framework, gravity isn't a force, it's the curvature of spacetime caused by mass and energy. One of the most exotic predictions of this theory was the existence of gravitational waves, ripples in the fabric of spacetime itself, created when massive objects accelerate. Einstein predicted that colliding black holes, merging neutron stars, or exploding supernovae would send gravitational waves racing across the universe at the speed of light. But Einstein himself was skeptical these waves could ever be detected. The distortions they create in spacetime are infinitesimally small, stretching and compressing space by less than the width of a proton across distances of kilometers. For decades, gravitational waves remained theoretical curiosities. many physicists doubted they existed at all. Others believed they might be real but would forever remain beyond human ability to measure. That changed on September 14, 2015. The Laser Interferometer Gravitational Wave Observatory, LIGO, consists of two facilities, one in Hanford, Washington, and another in Livingston, Louisiana, separated by 3,000 kilometers. Each facility houses an L-shaped detector with two perpendicular tunnels, each 4 kilometers long. The principle is elegantly simple but brutally difficult to execute. A laser beam is split and sent down both tunnels simultaneously. Mirrors at the ends reflect the beams back. If a gravitational wave passes through, it will stretch space in one direction while compressing it in the perpendicular direction. The two laser beams, having traveled slightly different distances, will be slightly out of phase when they recombine. This phase difference creates an interference pattern that reveals the gravitational wave's presence. The challenge: gravitational waves from even the most violent cosmic events distort space by only about 1/10,000th the width of a proton, 10 to the power of -18 meters, across LIGO's 4-kilometer arms. To achieve this sensitivity, LIGO had to overcome every possible source of vibration and noise: earthquakes, passing trucks, quantum fluctuations in the laser light itself, thermal noise in the mirrors, even the microscopic vibrations of atoms in the detector's components. It took decades of engineering, billions of dollars, and the combined effort of thousands of scientists to build detectors sensitive enough to measure spacetime stretching by less than the diameter of an atomic nucleus across a distance of millions of meters. Other observatories soon joined the hunt: Virgo in Italy and Kaga in Japan, forming a global network that can triangulate the source of gravitational waves by comparing detection times. On September 14, 2015, at 9:50 and 45 seconds UTC, both LIGO detectors registered an unmistakable signal. For a fraction of a second, spacetime rippled with a characteristic pattern, a rising pitch that increased in both frequency and amplitude before abruptly cutting off. Scientists would come to call this sound a chirp like a bird's call, but one that had traveled across half the observable universe. The source, two black holes, each about 30 times the mass of our Sun, had been locked in a death spiral in a distant galaxy. Over millions of years, they orbited closer and closer, moving faster and faster, radiating energy as gravitational waves. In the final fraction of a second, they reached orbital velocities approaching the speed of light. The gravitational waves they emitted increased in frequency and amplitude, creating the characteristic chirp. Then they merged, forming a single black hole of about 62 solar masses. The missing mass, if you add up the two original black holes, roughly 30 plus 30 equals 60 solar masses, the final black hole should have been 60 solar masses. But it was 62. Where did those 3 solar masses go? They were converted directly into gravitational wave energy via Einstein's equation E equals mc squared. Those 3 solar masses, the equivalent of 3 entire stars, were radiated as ripples in spacetime in the final fraction of a second of the merger. This event, catalogued as GW 150,914, occurred approximately 1.3 billion light-years away. But subsequent detections have found even more distant sources. The most massive and distant gravitational wave source ever observed came from a collision that occurred more than 5 billion years ago when the universe was barely half its current age. The sound, when you listen to the chirp, it lasts less than a second. It starts as a low rumble, rising in pitch and intensity before suddenly stopping, like the cosmic equivalent of someone strumming an impossibly massive guitar string once, then damping it immediately. It's the sound of spacetime itself vibrating like a drum. It's the sound of 3 suns worth of mass converting into pure energy. It's the sound of Einstein's equations made manifest. The detection of gravitational waves represents one of humanity's greatest scientific achievements, a triumph over Einstein's own skepticism and proof of our species' ability to measure the seemingly unmeasurable. Today, gravitational wave observatories detect mergers regularly. Each detection refines our understanding of black hole populations, neutron star physics, and the expansion rate of the universe itself. But more than that, these detections, along with the plasma waves of Saturn, the magnetic song of Comet 67P, and the pressure waves of Perseus, tell us something profound. It is a haunting symphony of colliding black holes, singing comets, droning supermassive monsters, and whispering planetary rings. It is filled with vibrations at every scale, from the microscopic plasma oscillations of dust grains to the galaxy-spanning pressure waves of cosmic behemoths. We have learned to listen. And for those who dare to tune into the cosmos, for those willing to decode the vibrations hidden in electromagnetic fields, X-ray emissions, and the fabric of space-time itself, the universe reveals its secrets through sound. These are the most terrifying sounds in space. And they are also the most beautiful.